when we play Wordle, we can come up with a couple different strategies to kind of automate this playing. We've just been running either the same word or just one round, right? So when I run this, we get the same guess every single time. That's not always what we want to do. You should be scoped outside. And that's not always what we want to do. We want to implement a little bit of automation behind this. We want to see the computer play itself, essentially. And so the easiest way that we can set this up is we already have a list of all possible words, so why don't we just randomly pick from it? And when I think of random in Python, I always reach, well, not always, but I usually reach for the random module. And whenever I import the random module, I'm always careful to import the seed as well as whatever else I want. The reason I import the seed is because random values are generated with a starting point from whatever, usually it's whatever your operating system, whatever the current timestamp is, so that it's always unique. If you have a unique starting point, the randomly generated value from that starting point will be different every time you run the script. But I set this seed because when I'm just playing around, when I'm just testing, I want reproducible results. I want the same result every time I run this script in order to have reproducible results. And the reason that's important is if I encounter a bug while using this random selection, I want to be able to rerun my script and see that same exact bug, and then I can go about and debug it. If my script changes, right, the underlying values of my script change every time I run it, if I encounter a bug once, when I go to rerun it, I won't be able to encounter that bug again necessarily. And I'm going to have to sit there and either rerun my script a bunch of times to figure out what that bug was and why it happened, or I could have just set my seed. And so I always set my seed to 0. You can do it really anything, but let's say my unknown word is a choice from my word list, and my guess is also a choice from my word list. We'll go ahead and go back to just one round of Wordle, and you can see here, you can see here that we get our output as expected. And so we see that I've guessed the word quips, however the correct word was peaks, and it's colored appropriately. Let's go back to multi-round Wordle, and let's see what happens when I take a random guess at every round. Well, now we have a real game of Wordle going on here, just with a random strategy. Now we're not playing it very well, but we can see that there's a lot more, there's variation in our words, which is at least aesthetically pleasing to look at, and it feels like a much more fully fleshed out game. But if you're playing Wordle, if you've ever played it, I know I'm in a group chat with a lot of people that I know. We play Wordle pretty much every day, and we always compare each other's scores. How can we go about designing a better strategy? Right? If I'm playing, I'm not just sitting there picking random words. I'm using what I see in terms of the colors and the status of each letter to perform some type of more educated guessing. So I'm not just going to randomly guess. Let's see if we can implement this strategy as a smart word, aptly named. So just like our random function, let's pass in the word list. And just to start things off, whenever I think of simulating something or taking multiple guesses, I usually think of a type of generator. So we can probably start off with something that's just really basics. For word and word list, and I'm just going to produce each word as it comes up. So let's see how this would be implemented. I would have a guesser, and that would be the instantiation of this generator. Pass it the word list, okay, and then my guess would be the next iteration of guesser. Yeah, and so here you can see this is fully alphabetic, right, because my word list is pre-sorted. That's how it was in the file on disk. And so you can see that I am changing my guess. It's no longer just randomly picking, but I'm iterating through each word in this word list. And I think this is a fantastic starting point, because if you think of how we guess things, if we iterate over every word, that means we'll have seen every word if we had infinite guesses. We only have 6 guesses, so we have to work within the confines of that. But what we can do, since we touch every single word, is we can take feedback from our results, right, from this color, and we can use that to filter down our search for the next word. So In this case, because I see A and it has a dark background, I know that the next word I guess just should simply not have an A in it. But how can we do this with this kind of setup that we have? How can we feed in a value back to our generator? And if you've seen our seminars and sessions before, you'll know that the way you feed back a word into a generator in order to operate on that value more and either apply some more filtering or some other computation or criteria is you turn it into a coroutine. And what we can do is I can actually pass results back into this generator using the equals here. So instead of calling next, I'm going to have to call guesser.send, and I need to send in the results. The results are in a fairly usable format. We've structured this right so that we get each letter and each status every time we do a check. And so I can just pass in that check from the previous guess. So this would look something like results equals, right, like that. We can concretize this. And right, this is where kind of having that flexibility is handy, right, since my check was a generator. And then if I want to keep everything else the same, I can just iterate over the results instead of performing a check again. And this works perfectly. Okay, I don't have any guess. Okay, great. So the thing that I need to send this first will always be none. But what I want to do, since I want to send this thing the results, right, these results, but these results only exist once I've guessed. This is why we always start by sending our generating a none value. This is priming our coroutine in this case. And so when we apply this pattern, we see that I've actually, my code's still running. All I'm doing now is just passing data back into this coroutine. And you can see that here. Now I am generating a guess, and then I'm providing my coroutine the feedback from that guess. How well did it do? What's going on with each letter? I just need to use these data to update some filtering criteria to make sure that my next guess is more zeroed in or is more efficient than my first. And so if we think about the simplest perspective or point on this, I would probably say the easiest way to do this would be, let's start with the lowest hanging fruit, and that is to grab each letter that is just simply not in the word. That actually gives us a lot of coarse grain information and will help us zero in on the correct word to choose here. So I'm going to iterate for each guessed letter and status in results. If status is not in word, we'll just go ahead and print that guessed letter, make sure we're locking things in. Okay, and now we can see all the words that just simply don't belong. What I can do is store these words, let's call them bad letters. Okay, and then I can set up some filtering criteria here. And the first thing that I'll want to filter on is if, let's see, if any letter in my current word, right, since I'm iterating through all of them, if any letters in my current word for L in results, no, for L in bad letters, then I want to skip that result, and I can do that just by putting that in here. And I need to actually append all these bad letters. Since it's a set, we go ahead and add it in like that. Ooh, okay. So now we can see that we're dealing with, or we're employing this coarse grain information. We guessed a back as our first guess, A-B-A-C-K. And what this means is now that I've implemented all the logic driving these bad letters, that means I should never see another word or another guess with A, B, or C. After this one, I should never see another word or guess with D, D-I-N-G, or A, B, A, C. And you can see that this pattern holds true, and my set of bad letters grows and grows. So let's see what my bad letters are by the end of all this. You can see that they just keep growing. Maybe I'll print it out. It's a little bit more filtered. You can see that the letters that do not appear in the solution keep growing. We can use a little bit more information here though, right? We've just implemented just one part of this. And since I know we're going to be implementing a little bit more, I'm going to use that conditions trick where I can just store a list of arbitrary conditions. And I'll go ahead and throw this over here. Okay. And I need to carry the not with it. Good. Okay. And then I can simply just check if all those conditions are met, we're going to yield the next guess. All right. The next part that we can employ, probably the easiest piece to employ, is if the status is correct. Status.correct. And just want to make sure this is working. Okay, so we have all the letters there. This will probably be another set, right? There's no point in having any redundancies or any repeated values here. So I'll go ahead and use a set. And the different thing about using the correct letters over the incorrect letters is that these correct letters also care about their position. So I need a way to pass both the position and the letter. And then I need to check, right, in my current guess, or what would be my current guess, is this letter in that specific spot? If it's not, skip this. This is not a good guess. If it is, then it becomes a valid candidate. And so what I can do is I can take my current position letters set here, correct, and I can add to it the guessed letter. But since I also need that position, I need to add in just a little bit more here. I can enumerate over this and seal that, and then I have access to the position of that letter. Okay, there we go. So let's make sure this is working. Print. Okay, so yeah, looks like we're getting some correct letters in there. We got S and E by the end, which seems right to me. We just need to add in the logic for that. So this would be if all, because we want to make sure every single letter is in the correct position, word of I is equal to the letter. For I, we'll say not I, that's a little, I like position better, is equal to L for position, comma L in. And when we do this, let's see if I can spell things, correct position letters. Okay, 2 values expected 1. I didn't add my I in here after I went through all the trouble of enumerating it correctly. And so what we can see here is that once we guessed a correct letter in a correct position, our next guess also had those same letters in that position. And I want to continue guessing just to see if this is working as I expect it to. We hit a stop iteration here, but you can see we got the guess correct. You can see once we locked in some greens, every guess after that had the same greens in the same spot, which means, to me at least, that my logic is working. We can even comment this out and see what happens to performance when we don't have that locked in. And you can see we don't arrive at the correct solution. We can also get rid of our coarse grain information and simply just keep guessing in sequential order. Once we lock something in, note that that has to be locked in. But by combining the both of these, we actually arrive at the correct solution, provided we can guess 10 times, which I know we can't do in a game of Wordle. But I also want to solve this stop iteration here. We're hitting this because our guesser has run out of results to perform. That's because we've hit the correct word, and that correct position filter is simply blocking out everything afterwards. And so we are no longer have any valid guesses left, yet we're still trying to send results in. And so what we need to do is simply just break out of this for loop. And we can do that by asking if all results, status is, what do I call it, status dot, if they're all correct position, then we'll break, and for underscore comma status, remember this is a tuple, the results are a tuple, or a list of tuples in results. Right, and we can even print the unknown there. Maybe that's a little bit better than printing U1. And we can see that we arrive at a correct solution. But there's even more information here. We can use the letters that belong in the word, but are in the wrong spot. And if my intuition is serving me correctly, we can perform this, we can do this in the same way that we did the correct letters, except we just kind of invert it. And we're going to need, we'll need a little bit more logic. So I'll add one more elif. If it's in the word, incorrect position letters, and we'll add the same thing. All right, and I just want to make sure that this is growing before I try and work with it. There we go. Okay, so it does look like it's growing. So after our very first guess, we know that K, here, let me put this before the yield. There we go. We know that after our first guess, we know that K belongs in the word, but not at position 4, right, or the end of our unknown. After the second guess, we got no more information. After the third guess, we know that E is in the word, and it doesn't belong in the 0th position. Additionally, it does not belong in the 4th position either. Neither does K. So if we iterate over this, and we perform a little bit of conditional checking, and let's see here, we will probably also want the same type of idea that we had before, where we were using the correct words. So we'll go ahead and I'll just copy this down. So if every single word, given the current position in the word, is not equal to the current letter for position in incorrect letters, let's see. So that seemed to smarten it up a little bit, but I do know even more information than this. The incorrect position letters tell me both that, hey, this letter does not exist in this position, but this letter also just exists in the word, just in general, just not at this specific spot. So I need to add a little bit more logic, and I'll say L in word. And I'll go ahead and parenthesize these so I know that this and should be joining afterwards, just very explicitly. And we can see here, let's go ahead and fix how this is printing out and just see how many guesses it takes us to arrive at the correct solution. Wow. I'll go ahead and I'll add some counts here. So for guess I, right, and I'll print that out. Wow, it took us 4 guesses to get to the word peaks. And so now we've implemented this much smarter, right, way of selecting words for Wordle. You could probably take this code and have it input any real game of Wordle that you would like to see, and get it in a certain amount of guesses. So we're picking the unknown word at random here, and then for when the user, or the player, is guessing, we're using this smart word choice that is exactly what I'm sure all of us are trying to do in our heads in Wordle, except we have the power of computers, the power of programming, and we're able to actually evaluate that same type of check we're doing in our head on every single word, or every single possible word in this version of the game. So let's take one step back from here, and I'm very curious. I want to know, if we play, right, if we play 10 games, how many games do we win? Let's see if this works out of the box. Okay, so we need to instantiate a new guess, right, per game, as well as a new unknown. And let's see, for guess I, yeah, that should work. And our results also needs to be instantiated to none for each fresh game. Now we can add in just a little bit more printing here. So each game will be separated just visually by an equal sign times 5. I know that's the length of the word. And we could abstract this away, right? We could play Wordle with 6-letter words. We could play Wordle with 10-letter words. It's just changing a few lines of code here. Okay, and I need to move that out one, separate the games, not each row. And then when I print the unknown, I'll go ahead and print 2 empty spaces before, just so it lines up with everything. Sorry, 1 empty space, because these are space separated. And there we go. We have played 10 games of Wordle. Let's see how well we did. We won that first one in 4 guesses. We won the second one, it took us 6. Third game in 3 guesses. Looks pretty good to me. We lost, okay, we did lose. We lost 2 games. We just had some poor guessing there off the bat. But if we look overall, and if we win, right, and call that variable wins. So let's print out our total games and our wins. And you can see we won 7 out of 10 games using this logic. That's not too bad. Let's see what happens if we bump this up to 50 games. 80% win rate. I'm not too upset about that. If I could complete 80% of my Wordles in, how long did that take? 3 seconds? I'd be very happy. But obviously it defeats the purpose of the game. But what we can do is, examining this output, I want to go back and figure out why we got some of these words wrong, why we weren't able to guess some of them. And my immediate intuition is telling me that our initial guess isn't a very good word, right? We're guessing the letter A twice, so we're not eliminating as many possibilities as we can. And if you are a fan of Wordle, you probably know that people keep their starting words very close to their chest. How do we implement this good starting word logic within the confines of the program we've already written? Well, I would probably take my smart word generator, or coroutine, and I would give it somewhere to start. I wouldn't let it necessarily start at the first letter in my alphabetically sorted word list. I would say, if start is not none, right? And then I would want to do something with my word list. I actually would want to, let's see, I could prepend it, meaning I would mutate the word list, but that's not necessarily what I want to do. And if you ever have an iterable, something that you don't want to mutate, you can always reach into iter tools, and you can use chain. And so in this case, I can chain, right? I can establish a new word list by chaining my start, right? And if, let's see, if start's going to be a string, I need to encapsulate it in a more traditional container type. And I simply overwrite it. That should work. And so this should run. Let's go back to just playing one game. All right, so that seemed to have worked. Now, let's try instantiating my guesser with a preferred starting value. I am going to share my starting word with everyone. One of my favorite starting words is stare. And I like it because you get the RST, which if you've watched Wheel of Fortune, RST, LNE, right? Those are very common letters in words. And then we get 2 vowels out of it, A and I. We could do something like store, S-T-O-R-E, to get a different set of vowels, but we'll start with stare, and we'll see if this works. So we did start with stare, and then immediately we went to Beck. So we got a little bit more logic out of our guesser here by starting with a good word. So let's go back to using 50 games. Let's see if we can do better than 40. Wow. I think the results speak for themselves. By playing 50 games of Wordle and starting with, albeit a good quote-unquote word, right? Everyone has their own word. we were able to get an extra seven wins out, right? Whereas if my guesser was none, I believe we were 40 out of 50. And so by simply just starting off with a good guess and then implementing the same exact logic that we have been using, we are able to make a much smarter program that gets us a little bit more wins. It squeaks out that 47 out of 50, over 95%. So feeling pretty good about our implementation about our smart word guesser. And we all did it with a coroutine, a little bit of filtering logic, and obviously access to every word, every possible word. But by using this logic, we were able to filter down from the, I think, thousands of words in our word list. We can check that really quick, down to just a few actual candidates for words that will win us our game. And so that brings us to the end of our session here together. I have had an absolute blast coding Wordle from scratch with you. And I hope that you take some of these concepts, some of the ideas that we might have, we actually haven't touched on since the beginning, but the idea of using an enum, right, in order to represent a limited number of states and as a way to map them to some meaningful programmatic entity, like mapping them to the background color, right, that we want to set. You can use this enum type to instantiate methods on its members as well as class methods for logic. One thing that I might change, right, if I had to keep working and coding and iterating on this, I have to unpack GL, status in many different places in my code. So I might actually have that be a named tuple. I might have that be a data class, depending if I want this to have some of its own logic. And maybe I would shift the coloring logic over to that entity instead. But since I was just treating it as a tuple, it was convenient for me to put that logic as part of my enum class. And so thank you all very much for attending. This has been an absolute blast. My name is Cameron Riddell, and this is Don't Use This Code, and this has been Coding at the Speed of Thought, Prototyping Wordle. Thank you very much, everybody.